Uranium, the primary element used in nuclear reactions, is found in two natural isotopes, U-238 and U-235. U-238 is not a fissile material, that is, it can't start nor can it sustain a nuclear reaction. U-235, which is only about 0.72% of the world's uranium supply, is the most important isotope for nuclear reactions. U-235 is separated from U-238 by a process called uranium enrichment. The ratio of U-235 to U-238 isotopes determines how enriched the substance is. For example, a ratio of 20 to 100 U-235 to U-238 isotopes means the substance is 20% enriched. When a neutron strikes a U-235 atom, it turns the isotope into a more unstable isotope, U-236. The atom is so unstable that it breaks into two smaller and faster elements, releasing 3 free neutrons and large amounts of energy in the process. The free neutrons can then be used to create more reactions or siphoned off. If the process remains unchecked, then the rate of reaction, and thus energy produced, can reach dangerous levels. In order to keep the reactions in check, materials known as moderators are used to slow down the speed of neutrons. Moderators are made of stable materials, for example boron, graphite and water, and are used to absorb stray neutrons. Both heavy water, which is D2O, and light water, which is normal H2O, are used as moderators. Nuclear reactions output energy in units megawatts thermal, that is usually just shortened to megawatts. All reactors create the same amount of energy per individual reaction, though as the power grids can only transfer so much energy at a time, a lot of power from fast reactors is wasted as surplus. Whilst nuclear reactors have no standard design, they usually fall into two standard categories based on net power output. Commercial power plants produce energy, making heavy use of low-enriched uranium and moderators to significantly slow down the reactions, allowing the power lines to transfer all of the energy to the grid. Research reactors, on the other hand, are usually fast reactors. Fast reactors use highly enriched uranium to create a chain of fast energy-intense reactions, and the main purpose is to be a supply of neutrons for neutron bombardment. The reactor at Lucas Heights, dubbed OPAL, standing for Open Pool Australian Light Reactor, is a 20 megawatt reactor that runs off 20% enriched uranium. The OPAL reactor primarily produces neutron beams. The free neutrons in a neutron beam have many uses. Neutrons can test the dynamics of materials at the atomic level by artificially inducing stress in the molecular structure. Neutrons can also be used to measure minute quantities of substance. By being fired at the substance, the subsequent radiation method can be registered and the mass and molecular structure can be measured. The core of the reactor, which is where all of the reactions take place, is a 35 by 60 centimeter construction, consisting of 16 fuel assemblies surrounded by water. The fuel assemblies are made of enriched uranium silicide plates, coated in aluminium. The core is separated into 4 quadrants by 4 moderator rods, with a 5th rod in the center. The reactor pool is connected to another pool, used for servicing the reactor and storing spent fuel. OPAL has numerous safety features designed to prevent the catastrophic chain reactions that cause meltdowns. The first mechanism is designed to completely stop all reactions in the pool. In case of the reactor overheating, cadmium control arms will drop down, separating the cores from each other and absorbing any stray neutrons. There are numerous backup cooling systems as well, which are in place to prevent the reactor from reaching critical temperatures. OPAL is housed in a steel containment building, which would seal automatically if any radioactive material leaked from the pool. The radioisotopes created by neutron bombardment have found a large market in the pharmaceutical industry, with the unstable isotopes being used primarily for cancer treatment. The OPAL reactor has also found a use as an important supply of irradiated silicon, which is used to increase electrical conductivity in computer chips.